Hi everyone, welcome to the meetup. I'm Martin Goodson from the sponsors Evolution AI, and today we have a talk by Lucas Beyer, who's a researcher at Google Brain in Zurich. As usual, we'll have a 40-minute talk from Lucas. We'll keep Q&A to the end. QA will be facilitated by Yaniel Cabrera, who is a machine learning researcher at Evolution AI. If you have any questions, please do add them to the QA. So we welcome any questions in the QA. And if you want to ask your question yourself, which we encourage, then please put your hand up and we will unmute you at the right time so that you can ask your question. And with that, I'm going to hand over to Lucas.
Yeah, hi everyone. I'm Luca from the Google Brain team in Zurich. I'm going to start with the worst talk opener you have probably seen. I actually have a little toddler, and today, just an hour ago, for the first time in his life, he threw up on me. So now he's sleeping and everything is fine, but in the worst case, it may happen that I will need to leave for emergency in the middle of it. But crossing fingers, now it's fine and he's well asleep. Okay, so here we will talk about, so I will represent you my line of work of me and close collaborators over the last couple of years. And this is all about learning general visual representation. I first give you some background and then some like past solution attempts and the things we currently have highest hope in. Because of the incident early on, I also didn't have enough time to properly hide all my slides that I don't want to present. So sometimes I will just skip through something briefly. Don't let yourself be disturbed by that. And we can always discuss about anything afterwards anyways. So now let's get started. General visual representation, what does it even mean? Isn't it just some buzzwords thrown together or not? So it means basically understanding of the visual world that is really good and really generic. And we're gonna see examples of what I mean by that pretty soon, like more concrete examples. Why do I even care about this specifically and not like other interesting things in machine learning, deep learning, and so on? Because I believe you need a good visual representation to kickstart basically all the tasks that humans can do and use visual input. This really good general visual representation is my midterm goal. My longer term goal is to be able to somehow contribute to having robots that any non-technical person that cannot program at all, like my parents or my kid, or maybe by then they can program, but can teach the robot to do something useful. My firm belief is that the visual input is a strong necessary part of it, but it's definitely not everything. Like other topics would be learning from demonstration, for example. Maybe the teaching goes by showing the robot what to do. Could be speech recognition parts, like maybe we need to just explain in words the robot what to do and he would understand it. It would be really cool. But for now, I've been focusing on the visual representation part first. Like that's the ultimate goal and motivation of basically all the research that you will see presented here. Now let's get a bit more concrete about this human or this visual representation and talk about the human's visual representation, which is like the gold standard of what is good. And we're gonna play a little game, not interactively, but please play along in your mind. I can show you here a few pictures. And I tell you, wait, have the laser pointer. I tell you these 5 pictures here, I call them class A. These 5, I call them class B, and these 5, I call them class C. And not much time has passed, like maybe, I don't know, 15 seconds. And I show you this picture now, and I'm pretty sure all of you can tell me, yeah, this is clearly class A, right? Even though you may not know what these are. I mean, you know these are flowers, but you may not be flower expert and have never seen those concrete ones in your life, maybe. Another example, very different. These are satellite images. I show you these here. I tell you these are class A. These are class B, and these are class C. Like the flowers, you have seen many in your life, right? Satellite images, you may not have seen that many in your life. Or like maybe they look like airplane images and you've flown a couple of times, but it's not something you're very familiar with. But still, I talked a little bit, and I hope that while I was talking, you had the time to look at them more closely and have a good idea of what would be class ABC. And if I show you this one, I believe most of you will say, yeah, this is class B. It seems to be like this, I guess it's a basketball field seen from the air, right? And then yet another level harder, and this is the last one. I show you these 6 images and say they are class A. I show you these 6 images and say they are class B. And then I show you this new image and what class is it. Now this might not be as easy as the previous ones, I think, or maybe for some of you, you're immediately, oh yeah, I get it. And some of you need to think a little bit longer, but then eventually you will all see it. Maybe by now you had enough time to say that this is class A. The objects don't matter, but the number of them matter. This is 3 objects, class A, and more than 3 objects. I don't actually know, it's always 5. Yeah, always 5 objects, class B. And this is what I mean by general visual representation. Like, I show you things that you may have never seen before, like this picture here, this rendering. But still, you're able to quickly, from just a few examples, be like, yeah, okay, I get it, and generalize well. Now, this is the goal. To work towards the goal, we need to measure progress towards the goal. So the first work that we did is called the Visual Task Adaptation Benchmark, or for short VTAB, where we tried, like, we discussed a lot and thought a lot of how do we measure progress to this, but basically this little game that we played is how we can measure progress, essentially few-shot classification. So in this benchmark, we allow you to train a model on any upstream data, we call this, like any data that you want. Think of pre-training. We provide a set of tasks that are very diverse, some of which you have seen just now before, but there are a total 19 of them, for which you have very few examples that you can adapt your model that you come with on, and then it is going to be tested on the held out examples of these. And then basically the average of how you perform on its test set is a measure or proxy measure of how good is your general visual representation. And then we use these words interchangeably, pre-training or upstream, and transfer or downstream. And you can adapt on these images however you want, on these few training examples. All right, so that is the context, the setting, and the goal, and how we measure progress towards the goal. Now, how do we actually walk towards the goal? And this, we tried many things over the years, and a few of them I'm going to tell you more about. A few of them I'm just going to briefly mention that we did and skip more details. The first one a while ago is self-supervised learning, where the promise is like you have infinite unlabeled images on the internet and everywhere else. So come up with some clever idea of that doesn't need human supervision of trying to learn some signal from these images and hopefully good representation. We relatively quickly dropped this idea because let's say you have a self-supervised algorithm. You train a whole bunch of models with it, but actually in reality there are many self-supervised algorithms even, so which one do you even pick? Maybe the latest hype, most hyped one. But then you end up at the end of the day with a bunch of models and you need to choose one that you actually want to use. How do you choose it? Like either typically you actually then fine-tune it or train a linear classifier on top on a bunch of labels. So there are labels there. So why not use them during the pre-training already? And this led us to the thought of semi-supervised learnings. Like, okay, for any task that you want, there are a few labels, or you can quickly create a few labels. It's not that bad. But still, there are tons of unlabeled images out there that would be nice to use. So why don't we combine both of these? And we created a method that we called self-supervised semi-supervised learning, in short S4L. It's basically saying, okay, you have your self-supervised task, just keep it. It may be good, but you have a few labels, so just throw them into the pre-training also. It's very simple. And that way you can turn any self-supervised method into a semi-supervised learning method, right? And the key finding there was that actually as soon as you throw in a few labels, the representation learned is actually much better, much faster. Like one commonly known but not too often mentioned issue with self-supervised learning methods, even the current one, is you need to train them much longer than supervised. And so actually just a few labels of supervision thrown into the self-supervision make the representation better, faster. Okay, so that motivated us actually to go back and go to fully supervised pre-training. And I want to talk about this one a bit more. But this was our first, let's say, bigger breakthrough or step where we had much better visual representation suddenly, which then motivated us into like, okay, now we know about this large scale pre-training. Now let's try to let this large scale data speak even more by building even more flexible models, which led to ViT and Mixer models that I'm going to briefly mention here, although I guess most of you are familiar with them. And then after this, I'm going to dig into a few more, I think, a bit more interesting questions of like, okay, now we have these big models. Are we done? What's left to do? And any researcher will always tell you, no, we are not done. There is stuff left to do because otherwise they are out of a job. Anyways, we're also never done. And then I actually would like to spend a little bit of time on a new, more recent paper from us about image text models, which simplify a lot this transfer stage. Okay, let's briefly go through it. Or briefly, I mean, in the last half hour. So the first thing was about this supervised pre-training then. And the bottom line is simple, or the takeaway message is simple. Pre-training on a ton more data, even if it's not directly related to your task, can be a lot better or can lead to a lot better models if you are careful about a few things. And these few things are also relatively simple, but not that often done, or at least back then were not that often done. I think now they are more common. The first one is simply, in quotes, be patient. So if you train large models on a lot of data, you really need to wait. So this plot shows one of our training curves. And it doesn't matter exactly what is, like y-axis is how good is the model and higher is better. And x-axis is time, like the training time in terms of steps here. And so you see it gets better. This was back then with the staircase learning rate schedule. So each step you see is changing the learning rate, like reducing it. And often you see what looks like a plateau and it's flat. And you're like, okay, why are you continuing training here? You could just decrease the learning rate sooner and be done sooner. So if we do that, we get this dotted curve and things are overall much worse. And to make things worse, if we zoom in, often this area, like zoomed in here, looks like it's flat and no progress is happening, but only if you wait a lot longer, you see that actually progress is being made. So patience is one important thing. The second thing is it's important to scale everything together. Here, just briefly, x-axis is dataset size from 1 million to 300 million images. Y-axis is accuracy. It doesn't matter what dataset, it's the same everywhere. And these bubbles are model size. And the important takeaway, this little blue bubble is ResNet 50, the standard one that everybody uses. If you increase dataset a bit, it looks like, yep, it's getting better. But if you increase dataset a lot, it's actually getting worse again, your model. And this actually, in the past, made many people not think that much of larger data for pre-training. However, only as you go to really large model, you see constant improvement as you increase the dataset size. And this light blue model is gigantic. ResNet 152, 4 times wider. This is like super slow, mega massive. I think it took us at Google, what is it, 2 or 3 weeks to train it. And we had a lot of resources. So it's not something you really want to do. But if you do, you get a lot of benefits. And these benefits are not just like state-of-the-art accuracy on all the benchmarks that it was back then, but also more interesting properties, like much better at this few shot learning, the little game that we played early on. Here, this, again, x-axis is model size, and the 3 different curves are the 3 different dataset sizes. And the y-axis is few shot with 5 examples per class, so exactly the game that we played before. So the green is with the 1 million images. It's kind of, it doesn't matter how large is your model. You're always performing more or less the same. Blue one is 10 times more images, but the interesting one is the orange one, which is again 10 times or 20 times more images. And there you can very clearly see the larger the model, the better you get even in few shot. And you also get much more robust models. Here again, same story with the colors, and here the added crosses are all the previous like fancy or established models. And this is one example of a robustness benchmark, which is ObjectNet, which contains a bunch of the ImageNet classes, but in very wide conditions, like what is it, office chair in the bathroom, on the floor, and things like that. And the story is the same again. Huge model, when pre-trained on huge data, gives you really big boosts in performance that were not seen before. So this was a breakthrough with not that easy to implement and actually do, but simple to understand concept, like pre-train larger models on larger data, both of these together, and be patient, and then you get a lot of benefits. So that basically made our group focus on that. And then, okay, this is getting SOTA everywhere. And then we were like, okay, so this is a very interesting finding. And now we are fortunate to have this large data to pre-train on. So let's try to make the best out of it. And then we spent quite a while prototyping different things to get a model where the model is much more flexible and maybe even less expensive to run than this giant ResNet that we had, because it was really clumsy to run. It uses a lot of memory, very slow, and so on. And one of the things we tried, and it ended up working really well and having really nice properties, is the following. Like in computer vision, there's convolutional nets have been done forever and are being done forever by everyone. It feels natural, convolutions on images. In language, RNNs and like LSTMs have been done forever, and it feels natural. It's a recurrent model on the sequence of text that is language. However, then in language, something happened, and there was this transformer, which feels much less natural at first. Like it doesn't respect the order of things, for example. But it has much higher capacity, and when trained on large data, it actually outperformed the RNNs by far. And so that's what we were after. We were also thinking, okay, this is interesting, and this model seems to have really high capacity, and we do have a large data here, so why don't we try this? And this led to ViT, the vision transformer. It's a very straightforward translation of the original transformer from language domain. Just instead of having words input into the transformer, we basically create visual words in the simplest possible way, by taking the image, cutting it up into a grid of patches. Each patch, we just see it as a sequence of pixels that we flatten, multiply to get to some dimension, like 768 dimensional embedding space. And that's it. These are our words. And then we do standard transformer thing. A learnable position embedding is added. We send it through a transformer encoder. We actually prepend an extra token, which is the class token, which will be collecting information throughout the transformer and then taken at the output. And then on top of this, the MLP head predicts the class. So this is the simplest possible way to adapt the standard transformer to images, or simplest way that we came up with. And this works really well. Here's similar images before, with x-axis being the dataset size, y-axis an accuracy. And in gray zone covers actually the numbers from the bit models that I showed before, like the ResNets. And the bubbles now are the ViT models. Again, like larger bubble is better. So this model performs a lot worse on small data. So this would be discouraging. Even on medium, or for our standards, medium-sized 14 million images, it's basically the same as the ResNet. There is not a clear advantage. But on the larger data, everything is higher up than the corresponding ResNets. Corresponding, I mean similarly slow ResNets. And importantly, the largest model that we can train here is better than the largest ResNet that we could train. This doesn't look like much here, but this is almost 1% difference in this data, in this regime. It means a lot. Furthermore, if we do a more controlled study of how these things train on the scale on the same data set, our internal JFT data set of 300 million images, but we take subsets, more and more subsets, and optimize at each subset, like the training. The interesting thing to look at here is gray versus blue, basically, which is ResNet's ViT versus Transformers ViT. At small data, again, the transformers look much worse, but if you look at the trajectory, it looks a lot better. And even our largest gigantic ResNet is still plateauing. Like 300 million images doesn't help it much more than 100 million, whereas the transformer continues increasing. So it is pretty motivating trajectory. Then, yeah, this was again state of the art. And this, we're gonna skip a few details on the model. So this motivated us to scale even further. And I'm gonna also skip on the details of scaling up, but basically there is quite a bunch of little implementation details, small modeling details, and so on that we need to take care of, mainly to reduce memory usage of the models such that we can fit as large as possible model into memory of the hardware. In our case, TPUs, but same story goes for GPUs. And then we did search for what is the largest shape that we can fit, and we went for a much larger than previously used ViT model. This doesn't really matter. Yeah, and one interesting thing that we found in this project that I would like to highlight, it's not directly related to scaling, but to this pre-training and then transferring setup. The performance of the model on the pre-training data set itself, we don't really care about it, right? This is just a task to get a good representation. We care about like the representation in this transfer setup or adaptation setup for the VTAB benchmark that I mentioned earlier, right? Like how quickly does it adapt to a new task and how well does it perform on the new task? Original pre-training doesn't matter. So we had this idea, and there is a proper intuition behind it, but no theory, but I'm sure there could be some, that the head of the model, like the big classification layer, during pre-training, we should treat it differently than the rest of the model. Because this head, after pre-training, we throw it away. It just contains the info of how to extract the classes from the pre-training, which we don't care about, right? And then for every adaptation, we have thrown away the original head and we attach a new head. What we care about is the representations before the head. And so here we did a proper study on weight decay and found that basically you can significantly increase the weight decay on the head during pre-training, which makes pre-training performance a lot worse, but then improves transfer performance a lot. And the intuition behind this is basically if you increase weight decay, you kind of force it to not have, like, how to say, you decrease the capacity of that part of the model, if you will. And so the model is forced to put much more information into the representation than in the head. Or another angle to look at it is if you, this is just hand wavy connection. But if you remember SVMs, SVMs actually, they have this margin, right? And the size of the margin is controlled by the regularization term, which translates to the similar effect as weight decay. So basically, by saying very high weight decay, we're trying to make the representations learned have high margin between concepts. And yeah, this is not directly related to scaling, but a pretty interesting thing we found in this project, and that made things a lot better still. And yeah, so then we took all of this together. We also went to our dataset colleagues and asked for a larger dataset and got 3 billion images, which also increased things, like improved things. And so basically we scaled to as far as we can go and get really good model with. Here's actually important that this is with ViT, the transformer, because ResNet, we just hit all the limits already where we were before. We couldn't further scale of limits as in terms of memory and slowness. And one interesting thing we found out during this scaling is actually that larger models are also more sample efficient. And sample efficient means just how many images they need to see before they have a good visual representation for us, like in the pre-training, how quickly they get a good representation. And here you can see 3 different model sizes. Blue is a tiny, very small model. Pink is a base model, which is medium size, let's say similar to ResNet 50. And this orange is a large model, still not the giant one. But what you can see here is that x-axis is how long has it been pre-trained. And basically, the larger the model, the quicker it has good representation. Y-axis is like, for these 3 different plots, we have 3 different ways of measuring how good is the representation in terms, again, of transfer accuracies, just in different ways. And higher is better. And so you can see that you get this accuracy with the large model very quickly after pre-training, whereas if you want to train a small model, you need to pre-train it for much, much, much longer to get similar accuracy. It's another interesting finding. Then, yeah, I will skip this briefly, but yeah, basically the bottom line is that we trained a lot of models of different sizes for different durations on different subsets of the data, and kind of found that there are similar scaling laws here in vision than were known in language already. Like basically log everything. Like you need exponentially more data, larger models, and so on to make a linear increase in performance. Yeah, I really no, okay. MLP Mixer was then the next step. We wanted to have even more flexible models, or basically get rid of even more hand-engineered design in the model. In the sense that in ConvNets, we have the convolution as like a hand-engineered decision. In the transformers, there's still this self-attention as kind of a hand-engineered like component-ish or core component. And then we wanted to see, okay, we have giant amount of data, so let's get rid of even the self-attention thing and have something fully learnable. So the most learnable thing is just a dense projection layer, right? So we tried to go as far as possible that still works with just dense layers everywhere. And that's how we ended up with the MLP mixer. There still is somewhat of a structure, but it's much more uniform than the vision transformer. I'm actually going to skip the details of the model here, but just jump straight ahead to the results. So this is, again, this plot of x-axis dataset size for the pre-training, y-axis measure of how good is the representation, in this case, few shot on ImageNet. And here, 3 different model classes. The black one is, again, the ResNet, or a ResNet from long ago in this representation, like 10 minutes ago. And then the colored one are mixer and vision transformer. The full lines are vision transformers, and the dotted or dashed lines are mixers. And then the colors are just different sizes. Blue is small-ish, similar to ResNet 50. Then we get large, and then we get really large. And basically, mixer always looks worse, but always keeps closing the gap. And with the largest model, there may be a crossing. So potentially, mixer is even better, like has even better scaling capabilities than transformers. Or we just have noise, and this was just a single run. So who knows? Maybe there was just lucky. So it's not clear if like this overpassing is consistent or not. So we went back to this 3 billion data and trained this comparable mixer and ViT at that size, and boom, it seems like mixer is further increasing the gap. So it seems that mixer is even better and more flexible at scaling up, and yeah, more work to do on seeing how far this can be pushed. All right, so we have 10 minutes left. Let me actually semi-skip this part. So we're getting better and better ImageNet results, and we started wondering, especially when we actually looked at some of these models, what they do and what they predict, we started wondering, okay, most of the mistakes didn't really look like mistakes. So are we starting to overfit to noise of ImageNet? Yes or no? Like we as a whole community, even as like for early top performing models. And I would just want to show you a few examples and then jump to the conclusion right away. So here are a few cases. One of those is the model prediction, the other one is the ground truth label. So here, one of them says ambulance, the other one says golf cart. If you look very closely, there is a golf cart here, right? Behind the ambulance. Here is a fun one. One of them says dock, and the other one says paper towel. This is a dock. If you look really closely, there is actually a paper towel here on the floor of the dock. And I'm gonna, okay, it would be fun to let you guess, but the model prediction is the first word and the ground truth label is the second word. So actually here the ground truth is a paper towel. This is the test set of ImageNet. So clearly the model makes much more sense in these cases. And here is a couple more again, like the label here is spacebar. Yeah, it's true, there is a spacebar in the image, but would you want to punish a model that says this is a desk instead of a spacebar? Not really. And these are not cherry picked. Like I just randomly looked at mistakes and of one of our top models, in this case, the large ViT model, and found a lot of such examples. Like I could fill tons of slides with such examples at this point. These were a bit more difficult to find, but the examples where the model and the label are both fine, like here, where example is when there's multiple objects, like the model says cauliflower and the label is box turtle. Yeah, both are fine. Or ambiguous things like, is this lotion or sunscreen? I don't know, both are fine for me, and things like that. And then I actually had a hard time to find examples where the model is clearly bad. I went through a lot of pictures to find the most ridiculous ones, like this one where the model says candle, but the label is dishwasher. Yeah, I mean, it's a special kind of dishwasher, but it still is a dishwasher. Or barbershop versus cinema, or loop versus wine bottle. And here the model says seat belt, but if you look, there is no seat belt. And so that makes sense, and the model is brimming up the seatbelt. But these were difficult to find. So this started this project where we went through the ImageNet validation set and basically relabeled all the images that are not obviously good. And like there's a long procedure that I'm not going to go through, but we made really, really sure that we relabel things properly for any problematic images, like here with two things and so on. And this we call the relabeled ImageNet, or the real labels. And then we use this to check, like, so what about these models? Are they really not perfect yet? Or is all the mistakes that we only get 90% on ImageNet, the remaining 10% are actually the model is still good and just the labels are not great? And the answer is a bit complicated, yes, but no. About are we done? And I'm gonna skip all of this and go to this one here. So y-axis is whether a human preferred the model's prediction to the ground truth label, yes or no, like how many percent of the images did a human prefer. So if the point is in the green, it means the model preferred the model's a human rater preferred the model's prediction more often than the ground truth label of the image. And then in the bottom, the other way around. Here the bottom line is basically the recent models starting with ViT and Noisy Student, like from 2 years ago, those, actually the humans prefer the model's prediction to the ground truth label. So it may be that we are slowly starting to overfit on ImageNet. And okay, then yeah. The next thing I also want to cover briefly. So I chose to cover more ground, but not go in depth too much on anyone, because I think if people are interested of in-depth things, we can have it later in the discussion, or obviously you can check the paper. So the next thing is we have all these benefits of giant models. We know how to train them and so on, but we figured out that actually nobody uses them, because they're just too clumsy and too difficult to use and too slow and everything, like even when we train them. So both internally in Google and externally in the public for the models that we released. So here is, for example, the download and usage counts of the different ViT models that we released publicly. The x-axis is like the size, and the the thing is, let's look at only the overall. Like the ResNet 50, the smallest model, is by far the most downloaded and used by people compared to the others, even though the whole point of the paper is you don't benefit from larger data if you don't also increase the model size. So with all the benefits that we show of large models pre-trained on large data, people don't actually want to use large models. And I can understand this. So we set out to do something about that, to somehow still get the benefit of large models into small models that everybody wants to use, like ResNet 50. And we explored many things actually over quite some time. But eventually the best thing we found is distillation from large model into small model. So it's distillation specifically for getting smaller models. And one thing we found out that some people may be doing already and think like, yeah, but come on, this is obvious. But a lot of people are not doing, and nobody ever explicitly investigated or called out in any papers that we saw, is that if you want to use distillation for model compression, you should slightly switch perspective and not think of like, you have this teacher model that has this dark knowledge hidden in the logics and the student learns from this teacher's super good knowledge kind of story. But rather, you have the teacher model that represents a function that maps images to logics. So logics is a high dimensional vector. And you want the student model to represent the exact same function as the teacher model. And if you take this perspective and the data that you distill on are support points where you can sample the function and where you want them to match, right? And you would like them to match everywhere in between two, hopefully. And if you take this view of distillation, then a few design decisions become clear that you should make them, and a lot of papers actually don't do them. So, or not just papers, also practitioners that we know. So one thing is that if you're thinking of distillation, the teacher model is huge and slow. So let me just pre-compute it once for the whole data set, its predictions, and then load them. This actually does not result in a function matching task because the student sees randomly augmented version of the image and should predict what the teacher predicted for a single fixed version of the image, like the original image. This does not result in a task that the student should represent the same function as the teacher, but rather a collapsed function. And there's a few other things commonly done in the literature that from this point of view don't make sense anymore and shouldn't be done. Instead, what we argue for is that you need consistent teaching. So the student and the teacher should always get the exact same view of the image, including the same augmentation, same everything, which means you cannot pre-compute the teacher activations. And furthermore, we should try reasonable ways to fill the space, like this sampling space that I told you the data set are sampling points in the space. And we propose just mix up, basically, to kind of fill the space between points. So if you do this, this is what we call the consistent part of teaching. And let me skip ahead. And you need patience again. So this task of function matching is a really difficult optimization-wise, and we think there is a lot of mystery still to it. But we found that basically you need to train with current optimizers for super, super long for it to work. If you do this, you get a really, really good student that gets all the benefits from the teacher. But yeah, so I'm going to skip this because in the last few minutes, I would like to briefly also mention our latest work, which we called LIT, Locked Image Text Tuning. And this is about few-shot transfer, zero-shot transfer. Let me just briefly give the background and then skip ahead to results right away, and then we can go to a discussion. So the background, you probably all know by now, contrastive image text learning, which was initiated, or not initiated, popularized by OpenAI's CLIP model, where you have a text encoder and an image encoder, and they both encode some text and an image into a space, representation space, and you want the representation of the text that matches the image to be similar and those that don't match to be dissimilar. right? This is the contrastive image text learning. And once you did that, then you actually don't need to do any fine-tuning for any new task anymore. You just take your model and describe what you want by writing the text and embedding it into the space. Like each class, you write it, like for example, a picture of a pink primrose or a picture of a pocket orchid or corn poppy. I think these were the three in the game that we played in the beginning. You just write this text and you don't do any fine tuning, no nothing. And you get a classifier out of this contrastive model basically for free. So this is a really cool property that we think is actually better than the fine tuning because it makes it much more easily usable. If you remember, the goal in the beginning is that any person can use it. And if we introduce fine tuning of deep learning models, that's not really something any person can do and has a lot of hassle involved. So this image text is actually a really cool way to make fine tuning in quotes usable by everyone. So we're looking for combining the best of both worlds because this is cool, but these models are not really good yet. Like Clip was very good for the first time for such a model, but if you compare it to how good are other models, I just compared to standard ResNet 50 on ImageNet, which is not good anymore nowadays, right? Everything I presented, we got much, much better models. So can we combine both? Can we have this property of just spelling out the text for the models that we pre-trained that are really strong? And yes, we can by what we call LIT tuning, locked image text tuning. The bottom line is really simple. We do the model pre-training as I mentioned before. We remove the classifier head. Then we take this model and attach a text tower to it. Like we take this image model that we already have, we freeze it, and we take a new randomly initialized text model, and then we learn this text model only on image text pairs, like Clip, basically. And this way we get a text model to go with this really strong image model and can be used to then create new classifiers, for example, just by spelling out the class names. And I'm going to skip the detail. Yeah, this is what I mean, right? Remember this picture where we had the adaptation, which is usually fine tuning. But once we do this LIT tuning, you don't need adaptation anymore, just spell the class names. And this worked extremely well and closed a lot of the gap, but not everything yet, to our like really good models when we fine tune them. I'm more or less at time. I'm going to skip ahead. Yeah, there is some cool properties with this, like multilingual text models that come for free when we do this. I do want to show very quickly a couple example images, if I still may, of this, because there is a few non-trivial cool things that happen. Like it really starts to understand the text and the image. Here we have an example where it says a blue car parking in front of green and pink walls is given much higher probability than a green car parking in front of blue and pink walls and other combinations thereof. So it's not just a bag of words being matched to the image. And this, my favorite example, a lot of vision transformers for many, vision researchers for many years, including very recently, I think Gianluca, are claiming like, all our models are not really good. As soon as you give them surprising things, like a cow on the beach, they don't work anymore. Well, that's not true. Our recent models have no issue at all with this, like these large scale models. Here's the example of the model where you just say a cow sleeping on the beach gets much higher probability than all other things like a cow on the grass and so on. Like it clearly knows this is a cow on the beach. Multilingual. And very final, and then I stop, caveat, whenever you see such demos, remember that the people making these demos write the texts. And by playing around with the text, you can also make misleading demos. Like, for example, here, if we write these texts, emoji yawn, emoji cry, emoji smile, emoji sleep, it looks really good. Yeah, emoji yawn is much better. The other emojis are also okay probability, but they are not yawning. But we can write other texts like grinning face, blah, 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 yawning face, and suddenly the results are quite a bit different, right? So it's not a free lunch that the model is perfect and completely understands every text. You still need to play around with the text that you write, but it is a nice interface writing text. And I'm going to stop with this one.
Thanks, Luca. Fantastic talk. I'm going to hand over to Yaniel now to conduct the QA. Audience members, please put your questions into the QA, and we will do our best to make sure that you get to ask them.
Yeah, thanks, Martin, and thank you, Luca, for that great talk. Very interesting topics. Okay, so do we have any questions from the audience? Let me just check.
I have a question.
Okay, go ahead, Martin.
So you spoke a bit about at the end about the distillation, and I just wondered. You were speaking a bit about quite a lot of different augmentations that you're doing, mix-up and other stuff. How much better is distillation working than just doing the augmentations on the original labels, the original data?
Yeah, yeah, we have, in this paper is actually, I'm proud that is our paper with the most solid ablations ever, I believe. I will answer all of these questions. And it's a lot better. Like we do all of the same augmentations also for training from scratch on ImageNet, for example, and it's by far worse than when you start adding the teacher. Why? Because even though with all of these augmentations, you still have one image or like funky variants of it, but one image mapped to one label, one concept. And this is still like with the augmentations, you let me show a slide actually for this. With the augmentations, you delay the overfitting, but it's still overfitting.
Oh, are you on mute, Luca?
Yeah, I think so. I think
you switched to mute somehow. I don't know how that happened. Luca?
Luca, can you hear us?
Okay, now you hear me, right?
Now we can hear you.
Okay, this is because I am not used to Zoom at all, so it muted me when I started presenting. Sorry. Yeah, so I was saying I have an answer to this in the picture, and essentially, as soon as you add distillation, you never overfit. And if you were to overfit, if you do distillation with the consistent view, as we mentioned, if you were to overfit, it would mean the student perfectly matched the teacher function. So this is great, we win. And to show this here, this plot on the left, x-axis is training or distillation epochs on ImageNet. 90 epochs is standard that people do. Maybe some people do 300 epochs, which is already considered long. Here we go up to 10,000 epochs. X-axis is log scale, so this is absolutely massive amount of patience. This model ran for months, I think 2 months or so. And the black curve is actually if you take basically labels the teacher's prediction, but not with the consistent view. And this is a really good teacher that, as I mentioned in the Are We Done talk, is basically as good or better than the labels. So it's essentially supervised learning with slightly better labels. And you can see that with the augmentations and so on, we start overfitting pretty late. But after more than 1,000 epochs, we still overfit. And things get worse again. But yeah, so if we add distillation to the mix, there is no overfitting.
And then just to follow up on that, are there some general patterns that you've seen in terms of the generalization performance of the student models compared to the teacher models?
Good question. Let me think. I think not. None that I remember, no. We didn't. I think we didn't actually. All right, so we didn't transfer here. Like, okay, this goes to your question maybe. Now I get it better. This is the one case of the talk where we don't care about a general representation, but we do the distillation after the transferring. So we have this massive model that is the teacher that's general and good. We transfer it to the task of interest. And this we do many data sets, even like we take practitioners, we even have data sets with just 1,000 labeled examples. We do this transfer, that works well, but still the model is giant and clumsy, nobody wants to use it. And then this transferred model on the task of interest, we distill into a student on the task of interest. We never actually explored the distillation in the pre-train to get a very general small student. That will be an interesting thing to explore still.
Thank you.
Okay, we have actually a couple of questions coming from the chat. Minaz is asking, she says, first of all, fantastic talk and fantastic results. And then she's asking whether if you're able to share at least a shortened version of the slides, because since you had to skip over some of them.
Yeah, I have an answer, and it's no.
Okay.
We actually have an approval process for talks, especially when they're getting recorded. And I did ask for this because I sometimes get asked about the slides. In principle, I could, but there is much more thorough approval process that I need to go through, which I simply didn't do yet and don't really have the time. Most of my slides are actually just screenshots of figures of the papers, just rearranged slightly. Yeah. And I feel a lot of them don't even make so much sense when I don't talk with, like, along with them. But yeah, sorry to say that I cannot share the slides as is.
Okay. Well, Minas, I guess you have to take a look at the papers. The screenshots that come from there. All right. So there's a second question. It's from Sarah, and the question is the weight decay trick during pre-train only helpful for a scaling transformer? And then have you tried or tested this approach with ResNet family model?
Good question. We haven't tried. I would expect it to work. Like, our intuition, why we came up with this and like why we think it works is not tied to transformers. And not even tied to scale, just to the fact that you have the pre-training, which you don't really care about itself, and then transferring to other tasks, and you reset the head, or like you drop the head and use a new one for each new task, right? That is the requirements to it. So I would expect it to work well for ResNet too. We just never tried because we kind of switched to vision transformers for most things. Yeah.
Okay.
It would be nice if somebody tries it and like says it works or not. Would be good to know. So just ping me on Twitter. Hey, I tried this. It works or it doesn't work with ResNet.
All right, Sarah. So if you try, let Luca know what the result was. You know, actually, look, I have a question myself. I think I saw in your slides that when you came to the ViT, the visual transformer, the model, the architecture with fewer words was outperforming the model with more words. So I think I saw the ViT 14 in your plot above in the performance of the ViT 16. Is that
Should we go
so?
back to the slides?
Sure.
That's now I should not forget to check the muting. Okay, now I'm not muted. All right, then the ViT model. Boom, boom, boom. Do you mean this slide?
Yes, yes. Yeah, like there, the orange, right? ViT is orange.
Maybe I should explain. So this number here afterwards is what you mean, right? So the okay, Okay. So the number afterwards is the nomenclature because, as you say, this corresponds, not indirectly corresponds to words because we cut the image into patches,
Right.
and each patch becomes a word, right? And so the number here is the size of the patch. So 14 means a patch is 14 by 14 pixels. So the smaller the number, the more patches we end up with. So this is actually, we increase the model size by reducing the patch size, which means more words.
Okay, I thought it was the number of patches, but it's instead the number of pixels in the patch.
Yeah.
Okay.
We actually went back and forth with what we should use as the number here, and we ended up with the patch size because it was a slight. If you change the input image size also, then it's more clear what happens if you say the patch size versus the sequence length. And yes, so this is actually a thing that is specific to vision transformers, and it is a little bit of a pet peeve of mine. Like if you say, okay, the patch size is, or slash sequence length is one of the things we can play with to change the model capacity. The other one is like just the model size, meaning number of layers and width of the layers, right? And this we usually denote by B for base, L for large, H huge, and then G for giant or something. And the vision transformers have this special property that you can keep the same model size, like B, but change the patch size, and you get a significantly slower or faster, higher or lower capacity model. Right? So if we take B32, it's much smaller and faster than B16. However, the total parameter count is basically the same because you just change the patch number, so the model itself is the same. Even more, if you have a smaller patch, you have slightly fewer parameters than if you have a larger patch, because the only parameter that changes is the embedding of the patch.
Right.
And for larger patch, this has more parameters. So ViT is a perfect counterexample that number of parameters doesn't always correspond exactly to model size or capacity. Just wanted to mention this is my pet peeve.
I have a question if I can jump in, Yaniel.
Yeah.
I just wondered about the generality of these results. So we've spoken about vision representations, but I think I'm right in saying that mostly you've spoken about image classification. So for things like the vision transformer, how important, in ImageNet, for example, how important is positional information? You can think of lots of tasks that may rely much more on positional information. And is it possible that maybe we're ignoring, like, positional information is not actually that important for these kind of tasks, and that perhaps it's a weakness of the ViT?
Yeah, this is very possible. And it's true, especially in the original ViT paper, we don't mention this at all, or don't investigate this at all, I should say. In the ViT paper, like the first scaling thing, we actually have a section on detection also, where we basically show, okay, if these better backbones and larger ones also then result in better detectors. But we didn't do this anymore for ViT. They yes and no. So we didn't explicitly do this, but there have been millions of works afterwards, which show like interest. Some show interesting properties, some show counterintuitive ones, some show like, oh, there is actually ViT models have, like some of them, a paper of some of my colleagues, Thomas Untertiner and others, have a paper that is like, actually it seems that ViT model retains location information better than ResNets. But is not measured in terms of like accuracy of it as a detector afterwards, but more direct measurement of locations of like the representations and their locality. I have also heard reports of like, no, this the representation of the ViT is really badly aligned with the input. So I think it's currently a mixed bag, and I have heard both feedbacks. And actually, me and collaborators have started looking at this more than we have in the past, which in the past was not much at all. I do think at the start, a lot of people were worried about this crude cutting into patches. This one I'm not worried at all about, because essentially, if you take 16 by 16 patch times 3 channels, that's 768, and that is the width of the smallest of our models. So this first cutting into patches doesn't lose information, and in principle the model could just like transpose the pixels and channels into the width of the model, and that's it. Yeah, but I think this story about like do ViT, like are they maybe just better for classification, or are they better for everything? Maybe they lose a lot of like localization properties, maybe not. I think this story is not over yet, and there's still a lot of work happening.
All right, do we have time for one more question, Martin?
Yeah, one last one.
Okay, yeah, there is one question coming from the Q&A. It's from Fabio. He says, many thanks for the interesting talk. And the question is, would you have any result on contrastive representation learning versus using a classifier and chopping the classification head off for transfer learning?
And then what? Like when you chop the head off for transferring, then you need to attach another head, and for the task you transfer to, right? And then you could either just learn this new head and keep the rest of the model frozen, or fine-tune the whole model with the new head. And both of these we actually do and have in the paper. One of them we call linear evaluation, which is just the new head is trained. That's why linear. And this we usually do in few shot case. And the other one is fine-tuning. I can show this one picture that should answer this question completely. Basically, if you can fine-tune on the task at hand, it's gonna perform still better. I'm just finding the slide and then jumping right to it. And sharing screen again and not forgetting to unmute. Okay, yeah, we're there. So this slide basically, I think, should answer your question. These horizontal lines are our top models that were pre-trained in classification way and then transferred in the standard classification way. In this case, like chop off the head, attach a new one, and fine-tune the whole model. In this case, are the horizontal lines. And this is the best that we know to do. And so the blue one is this contrastively tuned, or which we call it tuned. And it does not go as far up yet as the proper like regular fine-tuning way. It does compare favorably, like it does reach similar performance, which is not shown here. I just tell you from memory. It reaches similar performance to learning just the linear head and not fine-tuning the whole thing. I think learning just the linear head is still somewhat better than the contrastive, but not that much. The reason why we actually like this image text part and why we think this is the future, and I think a lot of people in the community think so, is like what I mentioned. It makes things much more accessible. You don't need like fine-tuning rows and so on. You just write down the text of the classes that you want, and boom, you have a classifier.
Fantastic, thank you so much. Again, Luca, we're over time, so we need to stop there. Thanks so much for a really interesting talk. Thanks, Yaniel, for running the discussion, and thanks to the audience for coming along. This talk, like all the talks, are recorded. Is recorded. You can find our YouTube channel. It's Machine Learning London YouTube. You can follow me on Twitter, Martin Goodson, where I announce the talks, and I'll also announce when the video is uploaded. So thanks again, and thanks to the sponsors, Evolution AI, and see you next time. Bye-bye.
Bye-bye.